So this meeting is being recorded. And we recommend you to add your names to the attendees list in the document that I have shared with you previously.
Maria, could you send again a link to the document? Because probably yes. I missed something. Thanks.
Thank you.
Okay, thanks.
Okay, so welcome to the 11th Embedded Working Group meeting. My name is Maria Merlan. I work in Proxima in product management with Pablo, who is the technical manager of micro-ROS, and we are together hosting these Embedded Working Group monthly meetings. Today, as you must have seen in the document, we have a very lively agenda. We will start this meeting by introducing how to apply hardware-in-the-loop testing for micro-ROS. We will introduce the continuous integration testing procedure that can ensure reliability for micro-ROS operations in any generic microcontroller. This will be followed by 2 live presentations. The first presentation will be covered by our special guest, Bartolomé Jiménez Vera. He's head of software development at Capra Robotics. And he will be presenting us a real use case of a prototype that is using currently micro-ROS. This prototype is at a pretty high technology readiness level, meaning that it's not far to be commercialized. So we will learn about this project, the platform, and how micro-ROS is being used in this product. And the second live presentation will show a demonstration using micro-ROS with the SP32 board. And this will be covered by Pablo Garrido from Proxima. And he will be illustrating the publisher creation and subscriber parameters and services. If you want to treat any further topic, please add them into the miscellaneous section of this document. I want to thank the participants for bringing us insights on a monthly basis related to micro-ROS features, demos, and potential products. So without further ado, let's start with the agenda. Thank you.
Okay, so I'm going to share my screen, my whole screen, in order to talk a little bit about the new
Pablo, you're muted. Pablo, you're muted. We can't hear you.
Now?
No.
Now, okay. I'm talking through the Maria's microphone. So I was saying that I'm going to talk a little bit about the new hardware-in-the-loop testing farm that we are preparing for micro-ROS here at the Proxima. We thought that hardware-in-the-loop testing is a kind of testing of a library of software of an embedded software that happens in a real hardware and emulates or tries to be as similar as possible as the final application. This is super important for safe critical application in embedded systems and improves the quality of our library and of the code. It also allows us to test in an automated way the changes and the improvements that we make in the library in, of course, the real hardware. The current state of the micro-ROS testing suite relies a lot in the ROS2 common testing utilities that are run both in GitHub in some of our repos using workflows that runs the tests of the different layers of micro-ROS in Docker, and also, for example, the RCLC runs its tests in the ROS2 build farm. So in this way, we are currently testing each layer of micro-ROS in a separate manner. But now what we want to do is to test all the micro-ROS functionality, in general, the micro-ROS API in a real environment. For doing that, we have thought about testing the entity creation and destruction, the quality of services, of course, the publisher and subscriber operations, services, parameters, the executor rate running on a board, on an MCU with the timers, with the hardware timers and everything, and all the functionality that micro-ROS offers as static memory handling, the type introspection, the domain ID changes if you want to create participants or nodes or publisher in different domain IDs, and the specific micro-ROS functionality like the agent ping, the epoch synchronization, or the continuous fragment mode. We are targeting the widest range of use cases. We are going to prepare a test bench that will run on UDP, serial USB, and it is super ready to include any other transport if we have that. And we also are going to test the most of the RTOSs that are supported in micro-ROS. In this case, FreeRTOS, ThreadX, which is a new implementation that we are testing, and of course the bare metal library implementation. The test will be run on Foxy and Galactic. I think that when we have this development more mature, we are also going to add a rolling hardware station for testing all the functionality in the rolling distribution. And this way, we are going, of course, to have a daily compilation, in this case, a nightly compilation of the micro-ROS client library and the micro-ROS agent. So a suite of tests are going to be run on the most updated micro-ROS suite, including the client and the agent. And finally, super quick, I'm going to show you a couple of details of how are we implementing that. We have here in the Proxima a Raspberry Pi 4B farm that have, I think that 30 units of Raspberry Pi 4B with an Ubuntu 20.04 server that, as you might know, is a tier 1 platform for ROS2. So we are installing ROS2 distributions in that Raspberries, and we are creating a ROS2 package that uses the common testing functionality of ROS2, that of course uses gtest, and it has a set of tests that uses the RCL-CPP to communicate with the second part of the test that is being run on a real hardware that runs the micro-ROS client. We are building a micro-ROS library in the same way that you build it using the micro-ROS tooling. And we connect this in an automated way, this micro-ROS client to a micro-ROS agent using different transport. And we test that the high-level functionality is working using RCL-CPP. In that sense, for example, if we are going to test the use of a micro-ROS publisher, we create a micro-ROS publisher in the client side, and we prepare a RCL-CPP subscriber that tests if the publisher is publishing correctly. Basically, that's it. We are doing an intensive work of automating all the procedures to program the board, and we are trying to prepare this schema as generic as possible in order to include the most of the boards that are currently supported by micro-ROS. And one of the coolest part, in my opinion, is that we are also integrating this with GitHub workflows. in that sense, when we release the new micro-ROS hardware-in-the-loop testing repo, just creating a pull request or anything in the GitHub repo, in the GitHub repo, the workflows will be run on custom runners that are here in our office. So in that sense, every change or every branch testing can be tested using just a pull request to our GitHub repo. These have some limitations because when you are using custom runners, you only can run one workflow per time. You are not going to be able to run multiple tests simultaneously, but it's interesting to have a real hardware operation testing in micro-ROS. So that are our plans. We are planning to release this at end July, if I'm not wrong. I think that when in the next embedded working group, or maybe in September, I will show you the system working, and we can provide more details about the functionality. I hope that you have found this interesting.
I think that's a super cool initiative. I remember 2 years ago we had a similar setup, prototypically with GitLab. At that time, GitHub Action Runners did not exist yet. One idea: could you also include some super basic regression tests in the sense that you record, for example, round trip times for a simple ping pong application or similar, that we see, let's say, if something goes wrong, if a certain change increase latency or whatever? Yeah,
I think that this is super interesting, and when we have the architecture prepared, everyone is going to be invited to extend the test suite. So, and the test suite is super easy to use because you only need to write an RCLC application and then the other part in RCLCPP for testing. I have also thought about integrating an embedded test suite, an embedded G-test, because there are some projects that provides the assets, macros, and that kind of things for running also test in the embedded side, not just testing the functionality in a separate way, just also running tests inside the board. But this will be a second part of the project, because we have to solve how to communicate the board with the test, with G-test, using some kind of non-intrusive communication way, such as JTAG or something like that. But we will talk about this more in detail in the following months.
Thank you. Now I would like to check if Bartolomé Jiménez is online.
Yes.
Okay.
I am.
Thank you. Are you ready? Would you like to share your screen?
Yeah. I'll do that now. Let me check.
For those who join later, let me remind you that we are recording this meeting, so you will sync up later with the first topic we just presented.
Give me 2 seconds. I'm trying to find out what should I be sharing, I think. This is it.
Yeah.
So okay, cool. Yes. So of course, thank you for having me here. I'm Bartolomé, Bart, it's easier. I'm the head of software at Capra Robotics. We are a small company, startup located in Aarhus in Denmark, alongside many other robotics companies that are here in Denmark. Our biggest asset, it's actually our wheel frame. It's quite particular. We carry the patent on top of this on the wheel frame. It allows us to go on really steep climbs, up to 30% climbs. We can go up to 15 kilometers per hour, could potentially drive. and we can turn on the spot, and we can also follow. It could be like a sort of a train sometimes. So it gives us the benefits of a differential drive, yet also the benefits of sometimes steering like a mix with Ackermann. So to begin, to drive more towards what actually drives to be interested on this, we make all the parts here. So we have 4 motor controls. We have the 4 wheels, have a motor. We develop software for the motors. They run on an STM chip. On top of that, we have fender boards. Those fender boards control brakes, some lights, some headlights, some other type of sensors that we have there. Besides those, then we have angle sensors that provide us the steering angles of the wheels, because they should be in theory all the time aligned, but it could happen that they're not, and we need to get that information. And besides this, we also have a main control board and a power control board, so that we get to actually split the logic between what is the main control, what actually the key power on, what does that do, and what actually controls the logic, the operational logic on embedded side. This also allows us to, from experience, we have the opportunity to actually all the whole control loop we have on embedded system, on the embedded side. So yeah, we have basically 10 STM32 chips around that body. The STM32 chips goes through different F4, F7, L4. There are different types there. More simplistic overview than just seeing those could be with this. This also shows what are we actually doing in each system. What communication are we actually also using between the systems. Here goes this because of the name of the model. It's a type of goat. Capra means goat in Latin. So you can see that on the left side we have the fender board, so ultrasound and light. Those are the boards that we communicate via, can open. Then the motor controllers also can open. The angle sensors also can open. The power control also can open. But the operation and control board, that one we have the opportunity. That one has an Ethernet output that we then, in that one is where we have our micro-ROS client running. That then communicates with Jetson Nano, that it's the main robot system component, which is basically what we focus on this part. So on the embedded side, we have all the control loop embedded. We have full control of that as well. So we have our buses go with the speed that we desire. We can do deterministic. We have full deterministic control on the optometry basically. We are using C++17 on our embedded side with some limitations, of course. We have no exceptions. We do no dynamic allocations and some other things that we had to custom use or constrain ourselves of using. We have implemented our own lifecycle manager. However, this lifecycle manager actually goes quite along. We follow the structure from the ROS side just to keep as close as possible to what we use across the whole top to bottom system. We have a very complex multi-thread system on the main control board. On the control board. We run on FreeR2S. We use FreeR2S plus TP as our Ethernet, so transport layer. We're building micro-ROS static library, and then right now we were developing with Foxy, but there's actually not many things constraining us to move to Galactic rather than just time to verify that everything still works. Our biggest reason to move to Galactic is the parameters server that we can use. With micro-ROS on the main control board, we have 4 nodes that can be soon 5. We have about 9 topics. between publishers and subscribers. We are not using services. At the time that we try to use, there are some subscribers that actually work as services, and at the time we tried to use them, there were some problems with the multi-threaded part, and then we simply stopped. I think everything's fixed now, but we didn't have the time at that moment to keep delving if it was stable enough or not. We are using the multi-threaded support that was added quite recently. We are using the time synchronization. We are also using the ping to agent functionality to be sure that when do we connect and how do we establish. And yeah, and as I said, we are building using the static library build functionality from the micro-ROS setup to later link it on our pipeline. This is quite on a simplistic. Yeah, I think of course I'm summarizing a lot of things. So our next steps are to move to Galactic, and we're quite interested in using the diagnostics. I saw that there was some work done on that, but at the time we didn't have time to see how it went and if it was possible to be used. And now we are keen to start looking at it finally. And just to show a bit of the robot. Let's see if this works. This actually is our prototype 4. Our idea is that we'll be releasing our prototype 5 after summer vacations, and then we'll be going out on the market. Yes.
Thank you.
That's pretty much. Yeah. I honestly kept it simple. My intention was also, I think, to just say that we've been interacting with the people through GitHub more than anything, with the people from micro-ROS. It's been quite an amazing experience through there. So
it's really interesting to know how micro-ROS is being useful and is being adopted in nearly commercialized products.
Mm-hmm. Yeah.
Now it is time for questions, comments.
I have a super quick question, because the other day in ROSCON France, we gave a presentation and someone asked Jan or colleagues in Bosch about the usage of C99 in the micro-ROS API. And I know that you are using C++ for embedded development.
Mm-hmm.
And I would like to know, in your opinion, which are the benefits of using C++, or which features of C++ 17 are you using in your development? Because we took the decision of making the micro-ROS API in pure C99, but maybe we should think about something in C++ or something.
Yes. Well, from our side, it's mostly like we have a lot of type-safe constraints that come with C++, and that we can just rely on C++ doing the thing that it should be doing. We also use a lot of templating. We don't use Atmel 8 or like some type of really constrained chip in which we don't have enough flash to have some virtual tables or have some templating code. The compiled code can be a little bit buffed in that sense.
Mm-hmm.
But the benefits of being sure that everything, it's how can I say it? It's the checks that we can acquire from C++. It's quite amazing. We have been, the people that I work with at Capra, we also made the same. We had the same question in the beginning, and I come from Mir working there, and then I have another person that also has a lot of experience working with C++, and it was simply there's no reason why C99 C++ nowadays doesn't have anything. You just have to have a lot of care about what you use and what you don't use. There, like, you have a lot of less headaches, I could say, by using C++ 17.
Okay, thank you. We also have here a question from Alexis, and he says that from where do you get the can open stack? Maybe you can read it from the chat. He's asking about your can open implementation. Hello, Bartolome.
Yes, hi. I for some reason got kicked out, or yeah, okay, I'm back. What was the question? Sorry.
Yeah, I was saying that someone is asking that from where do you get your can open stack, and
we have developed it ourselves.
Okay.
Yeah. We have developed every single library every single peripheral that we use, and every protocol we have implemented ourselves the libraries for them.
Mm-hmm. Okay, cool.
Okay. Thank you. Thank you for this great presentation. So now we go with the next live demonstration. Are you ready, Pablo?
Yeah, well, the other day, past week, we were at ROS conference and we did this demo, and we thought that it can be interesting to present it to you here in the embedded working group. First of all, what I have here is just an ESP32 connected to a LED array that have several LEDs, and they are connected in a daisy chain way. So we have used it to demonstrate how to work with parameters. We also have prepared some publisher subscriber for showing them in the ROS conference. We have the code here, so I hope that most of you are quite familiar with the micro-ROS API. So we are initting all the things, configuring the RMW options, and finally we are creating an LED node. This node have a publisher, a BSF4 publisher called. Oh, sorry, I'm not sharing. So I'm going to repeat everything. Now, you're seeing it?
Yeah.
Okay. What I was saying that I have here an ESP32 connected to an LED array, and then I'm showing the code. The common micro-ROS initialization code, the node creation and the LED node creation, and then we are creating a BSF4 publisher called LED publisher, and it is the type is STD messages header that have this is a super small ROS2 type that have a timestamp and a string, a character string. And then we are creating a subscription in LED subscriber that is of type int32. I'm going to show first the publisher and subscriber, and then I'm going to talk about the parameter server. One of the things that I have done here in this demo is to use the new micro-ROS utilities package that allows you to init message memory, type memory, using a static array. In this case, for example, we are telling the library to create a static message memory of type STD message header, and we are providing here the message, the output message. Here you have the output message. As you may know, in C, the string, the character of arrays that this type have is not init, so you have somehow to provide memory to that. In that case, we are generating here a buffer, and we are providing this buffer to the API. and also the size. And this way, this library is in charge of taking memory from that buffer and using it for every member of that header type that needs memory. In the case that it also calculates the size, so in the case that you don't have enough memory for all the members of the type, it will return a false or an error. In that case, a false, and a true in any other cases. We have documentation for this new API for static memory handling in our web page, because with this type, with this micro-ROS utility memory configuration, you can configure how long will be the strings, for example, or if you have a sequence of any other type, how long will be those sequences. You can configure everything. But in this case, we are just using the default configuration that init the memory, the strings to ascertain amount of characters, and the sequence to ascertain amount of items. You can configure the static memory creation. When we have a memory in our message, we are just using the same micro-ROS utilities to set the string. In this case, the string is the frame ID member, and we are initting it to LED node X. We are creating another set of string handling functions because the one used in ROS2, if I remember well, ROS IDL runtime C library will perform dynamic memory allocations if you don't have enough memory for handling your ROS2 types. With this micro-ROS string utility set, for example, it will check that your frame ID have enough memory for allocating this string, and if it has, you will not have any dynamic operation. In general, all the micro-ROS utilities API is super dynamic memory aware, in order to not to use it, and when you use it, you are completely aware that you are allocating things. The other member of the output message is a stamp, and so we are just filling it. So let's check. We are using the ESP-IDF, which is a tool for using the ESP32 as as Felipe Neves told us in the previous embedded working group. Now we are flashing, and here we have a micro-ROS agent. The code is running, so we have here our XRCDDS communication. That, remember, that is the default middleware for micro-ROS. Here I have prepared a ROS2 ready environment, so ROS2 node leaks, for example, and here we have our LED node. If we do a ROS2 node topic list, what's happening here? ROS2 topic list. Here we have our LED publisher and subscriber. We can see what is happening in the LED publisher. We are having problems here. I don't know what's happened. Maybe I have some misconfiguration in my computer. Here we have the LED string with the X and the timestamp. You might be wondering why this MCU have a timestamp, a Unix POSIX timestamp, and that's why we are using here the epoch synchronization functionality of micro-ROS. So the micro-ROS node can retrieve an Unix epoch time from the micro-ROS agent. The subscriber is just receiving an int32, and as you can see here in the subscription callback that is being executed by the RCLC executor, it's modifying the string in the output message. So if I open here, I hope that this works. If I publish something is happening today with this computer. Well, I'm going to talk about the parameters because this is not working today. It's just a basic publisher subscriber approach. In this example, we are creating a parameter server with the RCLC API. Remember that this RCLC API, it's only available in Galactic, in the newest micro-ROS release. And we are adding here the parameter server to the executor. We are also configuring a callback that will be run when someone in the ROS2 data space modifies a parameter. Finally, we are adding parameters to this parameter server. Those are the names and those are the types. We support currently only Boolean, integer, double, and that's all. And finally, we also have an API for setting the values of the parameters, just by telling them the name and the value. When someone modifies one of those parameters in our micro-ROS node, we are going to update the LED strip that I showed you previously. And for updating the LED strip, we are going to get the value of the parameters. We also have an API in the client side for getting the parameters. So in general, with this one, we are going to turn on and off the LEDs. With this one, we are going to set the number of LEDs that are going to be turned on, and the red, green, and blue values of the LEDs. I hope that this works, because with a ROS2 param list, it should give me all the list of parameters that we have here in the LED node. So, for example, we can do a ROS2 param set. We provide the node name, the parameter name, and the value. And we can see how the LEDs are turned on. For example, we also can modify the number of parameters that we are using, of LEDs that we are using, to 3 in that case. And we are using just 3 of them. For example, if we use type that is not correct, the functionality works. It says that type mismatch. And another thing that is super interesting to do using parameters with micro-ROS is, for example, the dump. ROS2 param dump LED node, and it will retrieve all the parameters available in a node and will create a file for us. If we cut that file, we have the current status of the parameters of our node. For example, now we can modify. We can do a parameter set. Let's modify the number, for example, to 4, and let's modify the color. In that case, I'm going to set the red color to 0. This is just from 0 to 1 number, and blue to 0.5. And now we have 4 blue LEDs. But remember that we have saved this file that has another configuration. So now this is super interesting because we can do a ROS2 param load in the LED node, and we want to load the previous state that is saved in this file. So we just use 3 red LEDs instead of the 4 blue LEDs that we were using previously. We think that this is a super nice functionality to have in micro-ROS because it provides a lot of flexibility to create applications in the embedded part. And that's all from my side. Here in that part of the screen, you can see the microcontroller's output, and you are seeing how the microcontroller is alerting us that some parameter is being modified, because of course in the callback that we have prepared, we have access to the parameter that we are modifying here with this variable here. So that's all. I hope that you have found it interesting despite of the subscription error, but let me know if you have any question.
One quick question, Pablo, on the console that you were showing, where you also got a type mismatch even when it was successful. That was
this is an error that I have solved today because we were not cleaning some variables. So here I have a pull request.
Okay.
So this is, I know that. The other day, someone in the ROS conference also tell us about that. So it's just cleaning a message.
Mm-hmm. Fine. Yeah, I think it looks awesome.
Yeah.
So
in ROS param, I often implement a type conversion to upset int into double type param. Can we do that in micro-ROS callbacks? I think that yes, because this parameter, this type have internally, this is a C99 struct that have the type, which is an enumerated, and then it have the integer value, the double value, and the Boolean value. So it's just a matter of casting the double value to your integer here inside the function. We are not using, I think that this is interesting to say that in order to provide details about the inner implementation, in order to not to redefine the available structures in the RCL parameter type support, we are using the same structure that the type support provides. Here you can see that this struct is just a RCLC interfaces message parameter. And that's why we are not using an union for having all the double, integer, Boolean, and all the thing in the same memory location. But by now, I think that this is a good solution and it works as expected. I hope that I have answered your question.
We have one added topic to the miscellaneous section.
Mm-hmm.
How to proceed when the client-agent connection fails.
Yeah, I think that this can be interesting because Bartolome and I have been talking about that. I hope that you are this one, Bartolome, right?
Yes.
Yeah.
That's
okay.
me.
We have been talking about that today. And if I'm not wrong, you are asking for the situation where when you detect that the agent is not longer available with the ping functionality of micro-ROS, and in this case you want to remove your entities.
Yes.
We were saying that, for example, when you call this API in the RCL, defining functions of every entity, here we are doing a couple of things, and here we have the code in our RMW. First, we are telling the micro-ROS agent to destroy the entity in the agent side. Remember that the micro-ROS agent always acts in behalf of the micro-ROS client. So when the micro-ROS client don't want an entity anymore, it should be removed from the agent. So we are telling the agent to remove the entity, and secondly, we are removing the memory that the RMW is using. This memory that is being removed here is not dynamic memory, it's a static memory. It's one of the items in the static memory pool that we are using in the RMW. But what happening when the agent have had a crash, or the agent is no longer available because the process have died? In that case, you are not going to run this session successfully, so you are going to have an error. And I think that is not good because, in fact, if you don't have the agent, the entity is not longer available, and your RMW will be releasing the memory. So in that case, here we are proposing to return a timeout instead of an error. So in the case that the entity is removed from the client side and you don't know what is happening with the agent, you will get a timeout. In other case, you will get an error. And another interesting point that I think that Bartolome was asking to us is what's happening when the agent is alive, but the communication channel is failing. In that case, you are not supposed to remove the entities, because when the micro-ROS client continues the operation or continues the communication with the micro-ROS agent that already have created the entities, it will know. So you don't have to finish and restart the entities if your agent is alive, despite of the time that the client and the agent have been without a communication. I don't know if this...
and the tricky part there is, how can I know what's the difference of them from the client point of view?
Yeah. From the client point of view, let me think a bit. But in general, in the micro-ROS agent is not a problem to make the same entity, because you have in ExaCDDS you have flags for telling from the client to the agent if you want to reuse, to destroy and create a new, or to make an error if you are reusing the entity. This is the ExaCD middleware. You have these 4 options. But in the RMW of micro-ROS, the default option is to destroy and create a new. So if you try to create the same publisher in the same node, the agent will destroy it and will create another one. So you will not have an error if you continue creating the same entities one time in the time. Okay. So if you detect that the micro-ROS client is not in touch with the micro-ROS agent, I will wait for some time and then destroy the entities and then try to create them then again.
Mm-hmm. Yeah. Okay. So
but maybe I think that it's interesting to talk. We can talk it in other day to provide an API in the middleware to check if some entity is already created. Mm-hmm. Somehow put it in the RMW API, because of course we are always super restricted by the RCL API, and this RCL API does not have the concepts of ExaCDDS. It has the ROS2 and the DDS concepts.
Okay.
That's cool.
So we have covered the full agenda. There's no more added topics. So we have reached the end of this meeting. And before finishing, I want to thank both speakers for your contribution today. We will be also sharing this recording shortly with all of you. We hope you find it insightful, and see you next time. Thank you. Bye, everyone.
Thank you. Bye-bye.
Bye.
Thank you. Bye.